Welcome back to Boson Buzz, where we make the universe's biggest ideas feel close enough to touch. I'm Monty Molecule. Today we're going to talk about a classic problem, the blurry picture. But this isn't a shaky camera phone shot. This blur is on the screens of the world's most powerful telescopes, and it's hiding entire alien worlds. We've discovered thousands of these exoplanets now, but for all our cleverness, they remain just that, discoveries in a catalog. Faint dots. We know their weight, their orbit, sometimes the gases in their air. But we don't know what they look like. Are they blue marbles? Brown wastelands? Striped gas giants? For decades, seeing actual details on a world light years away seemed like a fantasy. It would take a telescope so ludicrously huge, so impossibly perfect, that it belonged only in dreams. But then, a few brilliant minds asked a wonderfully simple, wild question. What if we don't have to build that impossible telescope at all? What if the universe already built the perfect one for us, and it's been hanging in our sky all along? We just had to learn how to focus it. This is the story of the gravity lens. To understand the genius of the solution, you first have to feel the weight of the problem. Let's pick a target, Proxima b. It's the closest known planet outside our solar system, orbiting the star Proxima Centauri. It's roughly Earth-sized and sits in the Goldilocks zone where liquid water could exist. It's our prime candidate for a neighboring Earth. But what can we actually see? Almost nothing. From 4 light-years away, it's a microscopic speck of rock and light, utterly drowned out by the nuclear inferno of its parent star. It's like trying to study a grain of sand that's glued to the glass of a lighthouse beacon, while you're standing on another shore miles away. You know the sand is there, but all you see is the blinding light. For years, the only way forward seemed to be to build bigger and bigger telescopes in space. But the math is cruel. To see the surface of Proxima b as more than a single pixel, you'd need a telescope mirror over 50 kilometers wide. Building and launching such a thing is a dream for the far, far future. It was a wall that seemed unbreakable. But the key to breaking it wasn't in an engineer's blueprint. It was in a century-old prediction from Albert Einstein. Einstein's theory of relativity tells us that massive objects don't just sit in space, they warp it. Imagine space as a taut rubber sheet. Place a heavy bowling ball in the center. The sheet stretches and forms a deep well. Now, roll a marble across the sheet. As it passes near the bowling ball, its path will curve inward, following the dip. In our universe, stars are the bowling balls. They warp the fabric of space-time. And light, our marble, always travels in straight lines. But when space itself is curved, straight lines become curved paths. A star's gravity can literally bend light. We've seen this bending called gravitational lensing for years with distant galaxies. But those are messy cosmic accidents. The new breathtaking idea is to turn it into a precision instrument. To use our own sun as the lens. The sun is massive. Its gravity creates a huge, smooth dip in space-time around it. And like any good lens, it has a focal point, a specific line in space where all the light it bends from a single distant star gets focused into a perfect image. But here's the catch. Because the sun's bend is so gentle, the focal point is incredibly far away. We're not talking about orbiting the Earth. We're not even talking about orbiting Pluto. To use the sun as a lens to look at Proxima b, you'd have to send a camera to a spot in space 4 times farther from the sun than Pluto is. It is, without a doubt, the most remote outpost humans have ever conceived. So, let's launch the mission. A small, incredibly tough spacecraft, more camera than ship, begins a multi-decade journey into the abyss. Its only cargo is a super-sensitive light sensor, a powerful sun shield to block the sun's direct glare, and engines precise enough to park it on a single imaginary line in the void. After a journey lasting a human generation, it arrives. It turns and looks back home. What it sees is not the sun, but a halo of light around the sun, a perfect ring. This is the focused, bent light from the entire Proxima Centauri star system. And if you look with exquisite care at a specific point on that ring, you'll find a tiny, bright smudge. That smudge is Proxima b. All the light from that entire world, collected and focused by the sun's gravity, is now hitting the spacecraft's sensor. The blurry dot has been transformed into a concentrated signal. Now, the camera doesn't take a snapshot. It starts a years-long vigil. It collects every single photon of that focused light, day after day, month after month. This is where the real magic happens in the data. The planet rotates, clouds form and drift over its surface, ice caps grow and shrink with seasons. The color and intensity of the light in that tiny smudge change infinitesimally. Back on Earth, scientists take this river of ultra-precise light data and begin to decode it. They aren't making a photograph. They are doing something more powerful. They are building a data map. By analyzing how the light changes, they can work out what's below. This wavelength suggests liquid water absorbs light here, maybe an ocean. That pattern suggests reflected light from a vast, sandy surface, a desert. A regular green-tinted shift could be from large forests changing with the seasons. They are, piece by piece, painting a picture of a world no human eye will ever see directly by reading the story told in its stolen starlight. The challenges are, of course, staggering. The journey is long. The spacecraft must be flawless. Aligning everything perfectly is a navigation miracle. But the promise? It redefines exploration. Success doesn't just give us a map of one planet. It proves that our sun is a universal tool. We could, in theory, send probes to different focal lines for different stars. We could scan the galaxy not for dots, but for worlds with geography. We could look for the telltale signature of an atmosphere like our own, or the unmistakable mark of chlorophyll on a distant continent. The search for life becomes a direct observation, not a guess. It turns astronomy inside out. Instead of building bigger eyes here at home, we learn to use the biggest lens in the neighborhood, our sun, by sending a single patient eyeball to the most distant vantage point we can imagine. It's the ultimate long-distance look. From an invisible speck in a sea of glare to a world with continents, oceans, and weather. That's the extraordinary, mind-bending promise of the gravity lens. It's the ultimate example of working smarter, not just harder. We're not just building a better tool. We're learning to read the instruction manual of the cosmos, which says a star isn't just a light source. It's also the most powerful magnifying glass imaginable. It reminds us that our greatest leaps often come not from forcing nature to our will, but from understanding its rules so deeply that we can hitch a ride on its own immense power. This idea turns our entire solar system into a scientific instrument, with a tiny, courageous probe as its focusing lens cap. If the thought of using a star as a telescope to finally see our interstellar neighbors sparks your curiosity, please help our channel continue exploring these frontiers. Give this video a like and subscribe to Boson Buzz. There are always more wonders just over the horizon. I'm Monty Molecule. Until next time, have a safe and curious week.